we've already learned about entropy in thermodynamics, and we know how ideal gases behave. Today, we'll combine these concepts to study a special type of flow, isentropic flow. When entropy stays constant and gases behave ideally, we get elegant relationships between pressure, temperature, and density. These powerful relations help us analyze high-speed flows in nozzles, diffusers, and jet engines. We define an isentropic process as one where the entropy remains constant. From thermodynamics, we know that this requires two things. The process must be adiabatic, so no heat is transferred, and reversible, meaning no friction or dissipation. We now step into the idealized world of compressible flows, where gases behave as ideal and processes are isentropic. These assumptions give us clean and powerful relations between pressure, temperature, and density. We're about to derive the isentropic relation. Let's be careful and precise. We'll begin from the first law of thermodynamics and apply it to an adiabatic and reversible process. We begin with a reversible adiabatic process, where no heat is exchanged. That gives us our key constraint. For an ideal gas, we can express this in terms of internal energy and temperature. To connect pressure and temperature, we'll use the ideal gas law. After substituting and rearranging, we get a relationship between temperature and volume changes. This leads us to our first isentropic relation, a fundamental equation for compressible flows. Here, gamma represents the ratio of specific heats, a key property that determines how the gas stores energy. In compressible flow, we often work with three key variables: pressure, temperature, and density. With two independent equations, like the ideal gas law and the isentropic relation, we can derive a relationship between any pair and eliminate the third. Now that we have our isentropic relation, we can derive how temperature changes with pressure and density. We'll start with two fundamental equations, the ideal gas law and our isentropic relation. Let's first find how temperature relates to pressure. We'll use the ideal gas law at two different states. Taking the ratio eliminates the gas constant R and gives us temperature in terms of pressure and density ratios. From our isentropic relation, we know how density ratio relates to pressure ratio. We can substitute this to eliminate density. After substituting and simplifying, we get our first key relation between temperature and pressure. For the temperature-density relation, we'll again start with the ideal gas law, but this time focus on the density changes. We can use our isentropic relation again, this time keeping the density ratio and eliminating pressure. After substituting and rearranging, we arrive at our second key relation between temperature and density. These two relations are powerful tools for analyzing compressible flows. They tell us exactly how temperature changes as pressure and density vary through a nozzle or any isentropic process. In many high-speed flow scenarios, like nozzles or expanding jets, heat exchange with the surroundings is minimal and friction is small. This makes the isentropic assumption remarkably accurate. Now that we've developed the mathematical tools for ideal compressible flows, now that we understand how pressure and temperature change in ideal flows, let's look at the bigger picture. These changes don't happen randomly, they're governed by some fundamental laws that apply to all fluid flows, whether they're isentropic or not. Let's start with mass conservation. If more mass enters than leaves, something must be building up inside. But in steady flow, what goes in must come out. We can write this as a simple equation. Next up is momentum conservation. Think of it like this. When you squeeze a garden hose, the water speeds up. That's because the pressure difference creates a force and force changes momentum. Newton's laws still rule, even in fluids. Finally, let's talk about energy. In a fluid, energy can take different forms. It could be the energy of motion, or the internal energy of the hot fluid itself. When there's no heat exchange with the surroundings, the total energy stays constant. It just shifts between these different forms. These three laws, mass, momentum, and energy conservation, work together to tell us exactly how a flow will behave. Think of them as the rules of the game that all flows must follow, whether we're designing a jet engine or understanding wind patterns.